So this is the last question from the curve sketching section 3.5. And here we have a trig function with a polynomial as well. So we have a combination here of types of functions. We have x and then we have plus 2 cosine x. We're given the domain, which makes our lives very easier, 0 to 2 pi. And what you can kind of think about with that is that that means that when we start from the left-hand side at 0, we would have 0 plus 2 cosine 0, and cosine 0 is 1, so we're going to get 2. And we can also look at the end point. This can be helpful to us, 2 pi. So when we plug in 2 pi, we get 2 pi plus 2 cosine 2 pi. And cosine 2 pi, as you probably know, is back to 1. So we get 2 pi plus 2. And then it can be not a bad idea to see what that is, and that's about 8.28. So we're going to start at 0, 2, and we're going to go to 2 pi. 8.28 is going to be our endpoint. In terms of intercepts, so when x equals 0, we already actually did that because that's the left-hand side of the interval, and we got y equals 2. It gives us that 0.02. So then we have our y-intercept at 0, 2. As far as possible x-intercepts go, we would be setting the function equal to 0. And in this case, I'm just going to tell you, I would obviously, if it was possible to check easily, we would do that. But in this case, there's not going to be any place where this x piece and this 2 cosine x piece are basically exactly opposite, giving us 0. And so we don't have any x-intercepts, no x-intercepts. So we just have a y-intercept here. So this function that we have is going to stay in the first quadrant as we graph it. And we'll see that more as we continue on. So for symmetry, let's just put in a negative x and see what happens. It looks like we'll have negative x plus 2 times cosine negative x. And we can see that we get the negative x. We want to remember that cosine is an even function, so it is symmetric over the y-axis. And so this is actually the same as just cosine x, doesn't change. And so we notice that the first piece is the opposite, but the second piece is the same. So we don't end up with any symmetry here that would be helpful to us in terms of graphing. So great. In terms of asymptotes, you can see that we don't see any vertical asymptotes because x is continuous, cosine x is continuous, so the addition of these two things is still continuous, so no issues there. We can think about the fact that as x gets bigger, we know that y is going to get bigger eventually as well, just because that x piece, the 2 cosine x is going to oscillate the cosine x between -1 and 1, just because of what we know about cosine. Multiplying it by 2 means that piece is going to oscillate between -2 and 2, just the values. But then when we add x, as x gets bigger, it's just going to keep getting bigger. So over time, as x gets bigger, y is going to get bigger as well. We're still only going, though, from 0 to 2 pi, so we're not going to have to go that far. But let's see if some of these derivatives help us. Let's see if that's something that's actually going to tell us something useful. So if you want, you can pause, take your derivative, make sure you get the same thing. Okay, so I get this, but I should have the negative. I shouldn't have waited on that. I should have just put that in, but I didn't. Okay, so here. So here's our derivative, and of course we're trying to find any critical values, places where the first derivative is equal to 0. So we'll do this, and then we do this, and then we divide. And so this is where that, knowing things about your trig functions is important. You should be able to do this fairly quickly thinking about when is sine x equal to 1/2 on that domain of 0 to 2 pi. So you're essentially taking that inverse sine of each side, but you have to think about that full domain 0 to 2 pi. So where it is positive 1/2 is going to be pi over 6 and 5 pi over 6, because that's where sine is positive. So you're basically, I'm doing it backwards here, but you're basically here on the unit circle and way over here on the unit circle. Between 0 and pi, you have two values. So we get that, and then what we can do with that first derivative, of course, is do a little graph. We'll get the graph of f prime here. Let's put on those two values that we think are important and just see what's happening on either side. So we have pi over 6, and we have 5 pi over 6. And we're going to put some values into our derivative to see whether the derivative is positive or negative, to tell us whether the function is increasing or decreasing. So don't forget to think of, well, let's do the sign chart first, and then I'll go from there. So putting in something that's less than pi over 6, you could put in, into the derivative, right? So if you wanted to, you could put 0 into the derivative. And if you do that, sine of 0 is 0. So 2 times anything is still, or 2 times 0, still 0. And 1 and minus 0 is just 1. So that's a positive value. Between pi over 6 and 5 pi over 6, I would suggest something like pi over 2. And sine of pi over 2 is 1. 2 times 1 is 2. But 1 minus 2 is a negative 1. So what we found so far is that the function is going to be increasing to pi over 6. It's going to be decreasing from pi over 6 to 5 pi over 6. And then after that, after 5 pi over 6, we are going to pick something like pi. If we put in pi, sine of pi is 0 again. And so we get the same thing, 2 times 0, and then 1 minus 0 is positive. There we go. So then after 5 pi over 6, we are increasing. Now if we put these values, x equal pi over 6 and x equals 5 pi over 6 back into the original function, that's going to give us the y values, the function values at those values. So if you put those in, make sure you're using radians. You're going to get about 2.26 here. You're going to get about 0.89 here, 89. And so again, make sure you can get those on your calculator. So those are giving us the y values for those x values, which are important because that is where the derivative equals to 0. So that's going to be some sort of local relative min-max situation. And then we just need our second derivative. So notice we're never going to lose derivatives here. We're always going to have derivatives because of the derivatives of that trig part. So when we do take the derivative of the first derivative, you can see that the first part, the derivative of 1, is just 0. So that's going to be gone. And then we take the derivative of basically negative 2 sine x, and that's going to be a negative 2 cosine x, because of course the derivative of sine is just cosine. And we're going to set that equal to 0, negative 2 cosine x, and not very exciting there, cosine x equaling 0. But I'm going to bring it up here. Now we can think about which values on 0 to 2 pi, cosine x is equal to 0. So of course you can always pause, think about when those values are. And we get pi over 2 and 3 pi over 2 for when cosine of x equals 0. And the same thing, let's do now a double prime chart here, double prime, second derivative, to test for concavity. So we'll put pi over 2, and we'll put 3 pi over 2. These are our x values. We're checking concavity on either side for possible points of inflection. So let's check for concavity. So we'll put in something less than pi over 2 into our second derivative. So if we put in 0, say into our second derivative, cosine of 0 is 1, and then multiply that by a negative 2, and we get negative. So we're going to be concave down up until pi over 2. Between pi over 2 and 3 pi over 2, we could pick something like pi, putting that into our second derivative. Cosine of pi is a negative 1 times a negative 2, and that's going to give us a positive 2, so we're going to be concave up. And then moving on, after 3 pi over 2, we could put in 2 pi, and cosine of 2 pi is back to 1, and times negative 2 is negative. So we're concave down. Thinking about our y values down here, we're going to have putting pi over 2 back into the original. Notice that putting in pi over 2 and putting in 3 pi over 2 back into the original, cosine of those values is 0, because remember now we're on our second derivative, so back to the original is back to a cosine. And so that whole piece is going to be 0. The 2 cosine x is going to be 0 for pi over 2 and 3 pi over 2, which means it's just going to be what we put in for x, and that's pi over 2 and 3 pi over 2. So we're going to have y equaling pi over 2 and y equaling 3 pi over 2. And of course, you want to find out what those values are in terms of, things that you can then put onto the graph. So come up with the decimal equivalents. But notice, again, we're concave down, and then we're concave up, and then we're concave down. So we have these points of inflection here that we have to think about. So we have our points where increase, where we have, like, as you can see, we have a relative max here because we're increasing and then decreasing. And here at this point, we have a relative min. So what you should do now is you should take just a moment before I show what this looks like, and you should put on your endpoints, and you should put on your points of relative max and relative min, and then you should also put on your points of inflection. And if you want, you can connect them, see if you can get that right, and then come and take a look at what we've got as the graph. And here we are. So here is our 0, 2, here is our 2 pi, and then that 8 something, 8.28 or so. And here's everything else. So we have the value that we already found, this pi over 6. So pi over 6 is here with that relative max. We also have this value right here. This is our 5 pi over 6 with about 0.89. That is our relative min. We also found that at pi over 2, which is about 1.7 or so, pi over 2, that was a y value. That's a point of inflection. That's here. That's about that 1.7 right there. And then there was another point of inflection, 3 pi over 2, 3 pi over 2. So that's, right about here, almost exactly. And that's 3 pi over 2, 3 pi over 2. So those are our points of inflection, here and here. We have our relative max here. We have a relative min here. So notice, let me switch colors really quick. We are concave down to here. Then you notice that we switch, and then we are concave up to here. So notice concave up like a cup. And then we are back to concave down like a frown. Concave down like a frown. So notice that difference in concavity. Notice the relative min and relative max. And then notice as well that we're just on that domain from 0 to 2. But what's going to happen now is that this function is just going to continue up. Because as x gets bigger, when x is 2 pi, 2 pi, is 2 times 3.14, so you're 6 something. That 2 cosine x is just not going to affect that first part of it, x, as much of the original function. And so it's just going to keep getting bigger and bigger. So it only has its changes that are happening there in the beginning. But that is an example of a function that has a trig part to it that we can graph and take a look at. And that's the end of section 3.5.